In this lesson, we're looking at logarithms in general, focusing in on the definition of a logarithm, having a look at some logarithm laws and some properties. So what we've got here at the top of the page is a base definition of a logarithm along with the log laws and properties. So the definition of a logarithm here is suggesting that in exponential form a to the power of x is equal to y is equivalent to log base a y is equal to x. So we're going to start by delving into that a little bit further. So basically I like to define a logarithm as a mathematical inverse of exponential functions. That is, just as subtraction is an inverse of addition, it's used to undo addition. Division is an inverse of multiplication, it's used to undo multiplication. Then a logarithm can be thought of as an inverse to an exponential function. So if we consider a simple exponential in the form y is equal to a to the power of x, and we look at that exponential and we understand the components, we know that this here is the base and our x is our exponent. Now if we want to write this in a logarithmic form, we can rewrite that as x is equal to log base a of y. So now what we're saying is that the exponent is equivalent to log of base a of y. So there's an equivalency here, and I'll show you with a simple example that you'll understand. If we look at 2 to the power of 3 is equal to 8, we can say that's equivalent to writing 3 is equal to log base 2. Now it's 3 because the exponent is 3. It's log base 2 because the base is 2 of 8. So these two statements are the same. One is in the exponential form and the other is in the logarithmic form. Another simple example would be looking at 3 to the power of x is equal to 27. We can write that in logarithmic form and we can say that x is equal to log base 3 of 27. So the exponent is equal to log of the base 27. Now the whole idea of logarithms is they allow us to isolate the exponent. So we can see here in both cases the exponent or the power or the index is isolated. And that is generally when we're going to use logarithmic functions and log properties. Now if we go back up and we look at our log laws and properties, we've got what they call 5 laws, which are really 4 laws and 2 properties. So we've got a basic set of properties. Log base a of 1 is 0 and log base a of a is 1, and we'll talk about that shortly. And then 1, 2, 3, 4 rules that we're going to explain shortly and look at some examples with as well. So now to look at the log laws and properties, we'll start with the 2 basic properties. The first one is that log base a of a is equal to 1. Now the easiest way to think about this is if we look at it in exponential form, then the exponent is 1 and the base is a, so we're saying that a to the power of 1 is a. And basically what we're saying in this scenario is that anything to the power of 1 is itself, so therefore log base a of a is always going to be 1. That's our first property. Our second property is log base a of 1 is 0. And again, we'll look at this in index form. Our base is a, our exponent or our power is 0, so we're saying that a to the power of 0 is equal to 1. And essentially this is our log version of that anything to the power of 0 is always 1. So there's our properties. In their rules, they say this is number 5. Not technically a rule, but a couple of log properties. Okay, so the first log law is this one. It's log base a of m multiplied by n is equivalent to log base a of m plus log base a of n. Now this is our addition log law. So if we add two logarithms with the same base and no coefficients, we can combine into a single log as a product. A simple example of this is we're going to evaluate log base 10 of 200 plus log base 10 of 5. So we can look at this as log base 10 of 200 multiplied by 5, which is 1000. And so this is log base 10 of 10 to the power of 3. And so that means our outcome, our exponent, is 3. Okay, so nice and simple is our first log law. Our second log law is log base a of m over n is equal to log base a of m subtract log base a of n. Now a simple example here will be we want to evaluate log base 2 of 32 subtract log base 2 of 8. So we can write that as log base 2 because they've got the same base and they've both got a coefficient of 1. We can say this is log base 2 of 32 on 8, and therefore this is log base 2 of 4, and 4 can be written as 2 squared, so the exponent is 2. The third log law is that log base a m to the power of p is equivalent to p log base a of m. So this allows us to isolate an exponent. So a simple example here is we want to evaluate log base 2 of 32. So if we write this as log base 2 of 2 to the power of 5, then therefore this is 5 times log base 2 of 2, and log base 2 of 2 is equal to 1, so it's 5 times 1, or just 5. Now, fourth log law is going to be the negative log law. So that's when we have log base a of 1 on n is equal to negative log base a of n. And so this allows us to simplify fractions within logarithms quite easily. So if we look at evaluating log base 2 of 1 on 8, straight away we can say that's equal to negative log base 2 of 8. And therefore that's negative log base 2 of 2 cubed, which would be negative 3 log base 2 of 2, and we're left with negative 3. Okay, so there's some simple examples along with the log laws and properties that you'll need to know, along with what a logarithm is. You'll need to make sure you understand these well. There'll be a follow-up video with some examples working through problems using the log laws and properties. Thank you for listening to the video.